Alrighty. Let's see. Okay. Seems to be alright. Let's wait one more minute. Okay, let me open the chat just in case if there are questions. If you have questions, whenever you have questions, whenever something is not clear, please ask. If you can hear me poorly, please let me know. We'll see what we can do. So I'll just try to give a little intro. Also, just small improvement. And the topic of today will be object-oriented programming. I won't be talking about the basics. What my goal is actually is covering the intricacies of object-oriented programming, trying to prove that object-oriented programming is a powerful tool to help us speed up development, make it more easy to understand, make it more maintainable. And how does it differ from functional programming? Is it any better than it? Or where does it excel, and how should it be best used? And what is the best at? So let's get right to it. So clean code, object-oriented programming. And I would like to start with misconceptions. And there's a funny quote. So it says that object-oriented version of spaghetti code is lasagna code. What does that mean? That means that with object-oriented programming, we inevitably have multiple layers. There's always some sort of abstraction. There's always some sort of dependency. Unlike in functional programming, where functions act by themselves and they're the only dependencies on functions, but not on layers which hold those functions. But is it a bad thing? Well, let's try and find out. So the first misconception that I hear in multiple levels of experience and development from developers is that objects are bags of data. And here you can see a link if you want to read more about it, a whole blog post about objects as data and objects as functions. But objects are not bags of data. Objects are bags of functions in object-oriented programming. Why is it like that? Because think, when we write an object, when we define our object, when we define our class, we communicate through properties. Through properties or methods. Properties are public, but they refer to private data, but they are methods nonetheless. So the access layer for our object is through methods. It should always be through methods. For a class, it should always be through methods. And you should never mix behavior with data. So data should be accessed through properties. And if you have small, tiny data modules with a few properties, they should be structs. And there's nothing more to it. So you can see an example. A class bag has a private list of items. And you might think, hey, it holds a list of items. But note that it's a private list of items. You won't be seeing that when you create a bag and when you access a bag. All you will see is a method get items and add item. And you will be able to access capacity, which is get only property. Objects, so another misconception is that objects have a big overhead, that objects are heavy to use, that object-oriented programming is slow, and that it's inefficient. But is it that way? So there is even a funny saying like banana monkey jungle problem, and a quote by Joe Armstrong, which goes like, when you wanted a banana, but what you got was a gorilla holding the banana and the entire jungle. So an extra layer of abstraction, objects, they do make things slower. That's true, and you cannot argue against that. That will definitely slow your program down compared to, let's say, pure, raw, no abstraction way. But the focus for ultimate performance is simply not there anymore. I mean, we have a ton of resources, and those little things like abstractions are not the bottlenecks of our programs. The bottlenecks are internet. We have the biggest latency waiting for a response from a server in a client-server application. We have biggest overhead in input-output operations, where we write something to a file, where we read a file, and so on and so forth. So even if objects do have an overhead, it's nothing that's significant, because there are things which impact it way more than a layer of abstraction and a little overhead created by an object. It's funny that many people say that OP is over-engineering things and creating unnecessary complexity, but that's not really true. That's not really how it is. Object-oriented programming, it helps us to simplify things. The problem here, though, is that there are many points where it can go wrong. With object-oriented programming, you might make wrong choices at choosing object design, at choosing the way you access objects, at choosing the way you let the object being created, at mixing relations between objects. There's just so many ways you can go wrong. But that's not a problem. That's just not really knowing how to deal with it. But knowing how to deal with it will make things so much better, and it will make it more readable, understandable, and maintainable compared to functional programming. Functional programming, on the other hand, is much more simple to design for. It might be, let's say, more understandable to someone who is more data-oriented, more input-output oriented, who looks at a problem as an input and an output kind of way. And functional programming is just a function, a bunch of functions which can be by themselves. So it's a whole different approach compared to object-oriented programming. But if OP is done well, it will do you very well. It will make your code much more easier to read, understand, and maintain. So object-oriented programming is not unnecessary complexity. All that it is bad design. When it is complexity, it means that it was poorly designed and a heavy violation of solid. And here you can see a class, Pocket Knife, which does more than one thing. It cuts, it opens, it shoots, it unfolds and folds, and it shouldn't do those things. Pocket knives should simply cut, fold, and unfold. Like, you take it and you cut with it. That's all that it should do. Simple. Keep it simple, stupid, and make it do one thing. On the other hand, object-oriented programming can go hand in hand with functional programming. There is a misconception that object-oriented programming is better than functional programming, and that is not true. For example, machine learning is an area which is best suited, best solved with functional programming languages. Languages like F# makes a nice combination with C#. You can make high-level API calls from C#, which calls under the hood F#. F# is a functional language, and you can do amazing things and much more easier than with C# for data transformations, for mappings, and things like that. So you cannot compare object-oriented programming with functional programming. Each for their own. Each solves a different problem. So choose your tools and don't enforce the same tool for different kind of problems. Just do a research, know what you need, and pick the right language, the right paradigm, or mix them if you need it. So what is object-oriented programming? We basically told what it is not, but what is it really? All it is objects to model real-world processes and business entities, like sky, like house, like chair, and many more. The key thing here is an abstraction made with classes, which allows us to create objects, entities through which we communicate with our business logic. And there is an excellent acronym for object-oriented programming, and it goes like this. Object-oriented programming is POO. It's not that kind of POO that you might first think. Basically, in French, object-oriented programming, OP, is an acronym for POO in French. And all that it means is that it's programming for others. And programming for others is information hiding and encapsulation. Simplicity, reusability, maintainability, and empathy. With object-oriented programming, we should think about the other person. We should try to think from a third perspective about our code and think if someone else will be able to use our code easily. What if we did something and our code suddenly needs maintenance? Will it be easy to maintain? Think about the other person who will have to take over. Do it right, and it will be a really nice feeling the next time someone comes and looks at your code. It's possible. It's not that magical. It's not that difficult even. You just need to have the right mindset and get into it. So, object-oriented programming is programming for others, if done right. And of course, now let's cover the 4 pillars of OP. It's encapsulation, inheritance, polymorphism, and abstraction. Encapsulation is hiding things that you don't need. And there is a quote by Dijkstra, a man who made many nice algorithms and who did a lot in programming, in data structures, graph theory. He said a quote that goes like this: simplicity is prerequisite for reliability. Which means that if we have lots of options to choose from, even though we might need them, things might go wrong in too many places. And by having too many options, we might make mistakes. And the more options we have, the more likely the mistakes will happen. So limiting what we can do, limiting the places that we can choose will make it better. Let me know when it's gone, and I have no idea why the echo is coming back. Is it still there? Let me know. I will also try to move a wire and see if anything changes. I appreciate that you tell me that it happens. Okay. Is it still there? So, encapsulation is hiding details, and normally in object-oriented languages you have 3 levels of hiding details. You have private, protected, and public access modifiers, and you can apply access modifiers for a function and a class variable, a property, or a field. Okay, sorry about that. I'll do a research, I'll do my homework and fix it. It will happen, sorry. Okay. And in C# we have one more level of abstraction, level of encapsulation. It's internal. And internal, what internal means is that the private scope for where something will be accessible is in the scope of a project. Everything outside the project, as long as it's tagged as internal, it will be not visible across the solution, only to that project. So private will be only visible in the scope of a class, protected will be visible in the scope of a class and in inheriting classes, and public will be visible outside the class. Internal will be visible outside the class, but no more than the boundaries of a project. So class should only expose all that is needed, and data should not be ever exposed directly. Data in a class is called fields, and it should always be private. The only exception where you have public fields is for structs. Structs should be read-only, and fields should be public read-only for structs, because you want simplicity for structs. But structs aren't classes, they're purely data, so it's a bit of a different thing. The key point that encapsulation tries to define is being minimalistic, having to use as little as possible. So things that we don't need should be hidden, encapsulated, wrap it, and hide all the details that you don't want to expose. This example right here is taken from Clean Code book by Robert C. Martin, where you have a map of sensors, and all you can do from a map of sensors is getting a sensor by its ID. But okay, Teklum asked, is internal only in that namespace? No, internal is not in that namespace. Internal is in a level of a project. If I, let's say, open my Visual Studio, so if I have auction class and mark it as internal, you see auction and is internal. And I'm in workshop lesson 3 project. So if I go to lesson 2 project and I try to access, I'll give a reference so that you definitely know that I have access to that one. And I'll be using the namespace as well. Right, so, oh, come on. Right, the gift picker, right, all good. I'll just delete those. Action, new action. auction, sorry, not action. Let me wrap it up so that others better understand it as well. So here I have auction and it's internal, and it says I cannot access class auction from here because it's marked as internal. If I made it public, it would be accessible from the other project. So just like fields and properties and methods by default are private, classes by default are internal. So if I remove that, I still cannot access it because the access level for auction did not change. If I write public now, I can access it. And of course, I would need to make this public as well. And that's all. So now here I can access it. So public classes are accessible across solution, and internal are only accessible across project. So here we have a big problem, and the problem is that map is a really awesome data structure, and it's powerful data structure, but look how many things that it does. We can clear a map, we can check if it contains a key, we can have an equals for comparing maps, we can get an element from a map, and that's actually all that we need. We can check if map is empty, notify all, put all, remove, get size, convert to string, get values, wait for it, and so much more. But we don't need any of that. All we need is to get a sensor by its ID. Get a sensor by its ID. And that's why we can refactor it into a data structure, into a class, into an object just dedicated for that purpose, for getting something by ID. We can nest the map underneath, under the hood. We don't really care. We can allow ourselves to waste the resources. But the point of it is that here we get a sensor by ID, and that's all our sensors class does. I remember that if you would look at .NET, Excel, Interop, you would also see something similar. And I was always weirded out by the solution that Microsoft chosen. For example, if you store a single workbook, it's a workbook. If you store many workbooks, it's not enumerable of workbooks. It's not array of workbooks. It's workbooks. Just workbooks class. It's not many workbooks, but it's workbooks class. And they chose it like this for the similar case because they encapsulated many things. Because adding a workbook is not the same as adding an element to the list. It's a different thing, and it's a process of its own. That's why it's important to have dedicated data structures for just the things that you need. Be minimalistic and don't expose things that you don't need. So for example, how can you determine what you need? Well, think about real-world examples. And in this example, in this code example, think what happens during auction, but think what really happens during the auction. All the auction itself does, it sells something. So when we have a design for auction in mind, we should design it like that. We should sell something. We should let auction sell things and nothing more. Nothing more. Auction itself might have a warehouse in it and other things, but it all should happen internally, externally, publicly. It should simply have an option to sell something. Accept the bids, sell the item. So instead of having everything internally, like accept the bid, buy, deliver, present, unpack, all we need is a cell method. So provide the same functionality that real life objects provide the same as much, but not more functionality. And so I would say that encapsulation is the most empathetic principle of object-oriented programming. With it, you basically make others' lives easier by writing clean code. It's the key principle for writing clean code, I think, for OP. Second principle is inheritance. And inheritance is extremely powerful. It lets us do generalizations of classes, sharing parent behavior with a child, forming a dependency on a parent. The problem with inheritance, but I personally consider it not a problem but a nice design choice, is that you can only inherit a single class. In my opinion, it's a good thing that you can only inherit a single class, and let's see why. Inheritance lets us do code reuse. After all, that's why we use inheritance. We don't like rewriting code. We want to reuse our code. If we wrote something once, we want to reuse it. The problem with inheritance is that it creates a dependency. So there is a nice saying that having a hammer, that inheritance is like having a hammer when everything looks like a nail. So if you have a function that you want to reuse on an object, you might think, hey, I will inherit that. But you shouldn't inherit code semantics. You shouldn't inherit functionality. You should inherit logical dependencies. And think about an animal class in this example. An animal can eat. Duck is an animal. It can quack and eat as well. But then when we think about rubber duck is a duck. Is it, though? It needs batteries. Is it an animal? Do animals need batteries? So in a case like this, inheritance doesn't work. And you cannot anymore use code like that by simply giving a parent class to a child class. It's not good enough. So there is a design rule that sounds like this, that we should prefer composition over inheritance, that we should split functionality that we just want to use and make it modular and reusable as possible, and have private dependencies of such classes in our class. Consider this as duct taping a bunch of small functionalities together in a single point, in a single body. Compose them. Make compositions of your classes. So here we have a gun, and a pocket gun knife is a gun as well. And the problem here is that if we want a pocket gun knife to also be able to, let's say, move, track a target, follow a target, or transmit a signal and do stuff like that, we wouldn't be able to. But if we refactor this to components, refactoring gun into a separate component, pocket knife into a separate component, now we can make a class, a crazy class like pocket gun knife. But we will have two separate classes. A pocket gun knife is a composition of two classes, of a knife and a gun. So the best way to use such dependencies is through dependency injection. But that's a topic for the next lesson. In this case, we simply pass a specific knife and gun, and that's how we create a pocket gun knife. And pocket gun knife does exactly the same as a gun and a knife, because all it does, it calls the private dependencies that it has inside it. And the last pillar, second to last pillar, is polymorphism. So polymorphism is way of functions of the same name behave differently. And there are two types of polymorphism. One type is where behavior is determined during runtime, and another type is where behavior is determined during compile time. So static polymorphism is a kind of polymorphism that exists in functional programming. Some people might not think that it exists, but it does. And all that it is method overloading. You will see this kind of polymorphism during compile time, and you won't need to run your program to see it in action. For different kind of input as in either different type or different number of arguments passed for method of same name, you will have static polymorphism. In other words, it's functions overloading. So here is a nice example how Granny behaves differently asking a question a man and a woman. Dynamic polymorphism happens during runtime for objects that derive from the same base type or implement the same interface. And essentially what dynamic polymorphism is, it's an is-a relation. So we have a teacher class, a teacher interface, and a teacher can teach. Student can study. A good teacher can do both teach and study. Lazy teacher just teaches. And that's also a composition-based approach to creating teachers. You don't have an inheritance for a teacher, but you inject dependencies for a teacher. Again, about this more in depth, we'll talk next week. And there is an excellent quote about abstraction and how or why it matters. So here it goes. From a very early age, we form concepts. Each concept is a particular idea or understanding we have about our world. These concepts allows us to make sense of and reason about the things in our world. These things to which our concepts applied are called objects. Which means that it's intuitive to abstract things away. It's intuitive to think about things in a black box. We use our phones. We know what they can do, but we don't know how they work. And that's all that matters to us. In programming, unless you need to create something to replicate the way it works, you don't really need to know the internals and the intricacies of everything. You need to have an abstract thinking when using classes. You need to know what they do without knowing how. So work on concepts rather than details is what abstraction says. And again, it's hiding details that is not needed. It's bundling tightly related objects and generalizing the specifics. So bundle the related things together and make an abstraction out of them. And to sum this up, I would like to say that there isn't really 4 pillars of object-oriented programming. Polymorphism, encapsulation, and inheritance is nothing more than an abstraction. Those are just complementary things for abstraction. So hiding what you don't need is thinking in an abstraction in a way that in order to use something better, easier, you will need to hide something. That's what the abstraction will need. Minimal functionality. Generalization, where you tell that a duck is an animal, is nothing more than an abstraction. You know that an animal can eat, can breathe. A duck can also swim. But when we talk about a duck, we talk about specifics and more details appear. You might not need those details. So abstract way of thinking in inheritance is nothing more than an abstraction. Polymorphism is very similar to inheritance. So we treat different types as one without the need of details. That's abstraction. So 3 pillars, not 4, because the other pillars make up abstraction. And what this all implies is that object-oriented programming is nothing more than a combination of well-thought abstractions. So seek for the best abstraction. And to finish this, I would like to say that C# is a true, pure, object-oriented language. Why? Because it derives, everything there derives from an object. In Java, for example, even though C# derived from Java, Java doesn't have that way of abstraction, that way of inheritance. Java primitives like integer, string, they don't derive from an object. They do have a wrapper class which does that, but it's not really like it is in C#. So C# is a true, pure, object-oriented language where everything derives from an object. And that's why there we have those overheads and those people saying that C# is a heavy language. But again, I'll remind you that those things don't really matter when we look at the big picture. And that's all I wanted to talk about today. And the workshop will be probably either tomorrow or on Friday, this Friday. So do you have any questions? In the meanwhile, I'll give a link to the slides so you can read it yourself. All right. If you have any kind of suggestions, any kind of things that you didn't like, anything that you liked and would like to keep it that way, something that you hated especially, I would appreciate that you could tell me all of it, and so that I can improve upon the quality of both stream and the slides, and so on and so forth. All right. It's really nice to have images because our brain, when we read about concepts, about new information, we immediately try to make associations. So when we see an image, we can associate a piece of info with an image, and images are what helps us better remember. And yes, it will be at the same time. And yes, it's a big delay. Not a big delay, I would say 15 seconds. I will need to work on it and figure out how to make it better, if there is a way. Alright, so I enjoyed it all and made some notes for what I need to dig more into and learn. Thank you. Thank you too for your attention. So that will be all for today. Thank you all and see you next time. Bye bye.